So knockdown factors. What is a knockdown factor? Let's start off at the beginning. Before we get into what is a knockdown factor, how do we use them, why do we use them, all of this comes down to the crux of it is it's about statistics. It's about understanding the mathematics of data. Data is everything for us, and the more data we have, the more useful that we can find the data to be in terms of making decisions about the future of a product or a process. Engineering statistics in particular, it's about using these statistical methods, which is some form of maths, to try and control, quantify, or key thing for us here is about the predictability of engineering operations. And predictability is quite an interesting word, because if it's not predictable, then how do we know what to expect out of it? So I know you've started to do things with CAD. Some of you might have had some experience with finite element analysis in CAD before, but otherwise you've definitely done calculations of stress, strain, etc. with me, if not some of the stuff you've done with John in science. The number that we're using for Young's modulus, for ultimate tensile strength, whatever it needs to be, that number, we choose a number randomly, or in reality what we do is we're using a predicted number, or it's some kind of statistically valid derivation. So in your assessments, you've done some nice work now with what does stats mean in engineering and materials, so hopefully this is nice and clear. You've done mean, median, and mode. A few of you have done some really good work with coefficient of variation and standard deviation, but all of these words are all methods in which we can acquire and analyze data. So a knockdown factor is then, if we use this gathering of data, this engineering statistics, we can then apply methods to assess or predict, back to that keyword predict, what might happen if something happens to a material. So for example, the ultimate tensile strength of a material, is it affected by temperature? Is there a knockdown factor that can be applied? We'll sometimes call these knockdown factors a safety factor, but in reality, all of these terminologies are all focusing on how do we change the real data to make something predictable, or how do we make something give us a higher level of confidence. So these slides are, the next few slides are a bit of an overview. So coefficient of variation, this is quite an interesting calculation in terms of looking at creating a ratio of standard deviation and mean. So when you've looked at mean for ultimate tensile strength, yield strength, and percentage elongation, the mean is obviously then dependent on what kind of value in terms of magnitude that you're talking about. So an elongation will maybe be single digits, whereas an ultimate tensile strength is in the hundreds times 10 to the 6, if not thousands. So if we then have a standard deviation calculation of that, then you can't really compare the deviation of ultimate tensile strength with elongation. What the coefficient of variation does is it allows us to compare the ratio of those two numbers. So if the numbers are very high, like ultimate tensile strength, the ratio of a very high number is comparable to the ratio of a very low number. And it's really useful to be able to compare variation in things which are not normally comparable. So you can't compare the standard deviation of ultimate tensile strength with elongation, but you can compare the coefficient of variation. So that's the crux of how we use it. And there's a couple of examples here. So just showing the different types of data sets in terms of their magnitude, a lot of variability, and not a lot of variability. Standard deviations, therefore, are not really comparable. Averages are completely non-comparable. But we can then use this coefficient of variation to look for the difference in those two values. Coefficient of variation, by the way, is not something that I'm expecting you to necessarily heavily use throughout your degree. What we're really trying to do is just make sure that you're armed with some tools that you may find a use for at a later date. Personally, I've used coefficient of variation to compare performance of forgings over time and things like that. So minimal usage professionally from my end as well. So, but it's really just there for information. So next up then, confidence. We talked a little bit about this already. I think during semester 1 when we talked about data and we was looking at magnitudes and quality of data. You hopefully have heard of Six Sigma, which is one of the most common phrases used for confidence intervals. But basically, what this confidence thing is about, how much can we trust our data? And we normally talk about these things as confidence intervals. More often than not, confidence interval is one standard deviation. So Six Sigma, for example, is 3 sigmas either side of the bell curve, which means 3 standard deviations to give us this high level of confidence. I have a couple of slides on that in a little bit, so we'll come back to that point. So this is about a 95% confidence interval, range of values that could be 95% certain. So if you have, on this graph, we've got 5 values. So the range of those values for a 95% confidence interval is high because there's not a lot of data and there's a lot of scatter. If we double it, so we go from 5 to 10 data points, we can have a higher, we can have the same amount of confidence, but over a lower range, because actually the spread is showing more consistency. And then if we get to a stage where there's 150 data points, we can be really quite certain that 95% of them will meet a certain point. So all that we're trying to get out of this is high confidence needs a lot of data. Hopefully that makes sense. We'll move past this. Statistical significance. So I've mentioned statistical significance before. We talked about this for your data, about how many data points are needed, etc. But all this slide and the next couple are really trying to do is just add a little bit more of that theory. So the significance level is something that when you're looking for data or you're looking at acquiring data, it's something that you would you want to kind of set, or you want to have some kind of target of significance at the earlier stage. So this is then, it's a threshold in which you can determine that data to be significant enough to be valid, if you like. So we normally call this a p-value, and it's your this p-value is what we set as a target then. So I mentioned it here. The probability of observing the differences seen in your data is 5% based on a 0.05 p-value. These are standards, I suppose, or these are things that we would normally expect to see. If you want higher confidence level, you then have a lower p-value. So the more confidence you want in the data, the lower the p. So high confidence in your data, you want 0.01, which is what we used to aim at in aerospace. This was manufacturing defect flaws. So this is where we start talking about how many parts will fail per million, etc. So we want very low values here for p because we want really high confidence. Hypothesis-driven experiments. So these are we're a bit more of a finger in the air, a bit more, I'm going to have an investigation of this because I think this will happen, then a 0.05 is fine. Again, not something I'm expecting us to take forward too much, but it's just good to know that if we're ever looking at data, p-values for significance do exist. So then, getting towards something that I will expect us to be touching on more and more in the next couple of years, process capability. So this is not just a term that we will say randomly, this is a statistically derived setup. So this is how we apply statistics to manufacturing, and this is where I do think that we have a bit of need to do this going forward. So the stripping all of this back and looking at what stats are considering, we have a variation of data which shows that the process isn't controlled. So if there's not that much control, then the next data point is unpredictable. If it's predictable and controlled, then it's mathematically accepted. If it's uncontrolled, then we need to do more testing to validate that it's going to be okay. More testing will take time and absolutely will definitely take a lot more money. So for a supplier into top level industry, if you can show that you can control your processes, then you have an advantage over your competition, but also you can then reduce the amount of cost and time in testing. So again, this is another one which we have a number which we will use, and process capability is absorbing all of those points above, and what we want to see is a minimum value of 1.33, and that 1.33 comes from a combination of process control and process capability. So these are the things that we'll look at now. So if we're in control of our manufacturing processes and we use statistical process control, which is the first important stats-based thing we'll talk a little bit about. We won't overcover through the next couple of years, but it's something that you definitely look at more on a master's level. So this SPC, statistical process control, is the first step, but it isn't enough. Just because your process is in control doesn't mean that it doesn't produce out-of-spec parts. It just means it's consistent. So what we need to make sure we do is we need to be able to meet the spec, whatever that spec is, whether it's a mechanical performance value or it's a quantity of failures, etc. Then we need to then add on to that. So we need to make sure that we are in control, but then we're also capable. And that's how we can repeat and be consistent in our manufacturing processes relative to the customer requirements. So that's the important extra step. It's not just about being in control, it's about meeting the requirements and being consistent. So this is where we get into these bell curve graphs. And this is linked to something that we've definitely talked about before, about spec limits. So whenever we've talked about data, I've always asked the question, if we look at a value in a spec sheet, where does that number come from? And that number is always the spec min. So that's the minimum expectation of that material in particular, is what we normally look at. So when we have this lower spec limit, these are the values that we already have. The reason they give that as a limit is because they have a 6 sigma level confidence that all of the data will be beyond that. So the actual true mean of our test data will always be higher than that lower spec limit. And the lower spec limit is set or calculated based on making sure that we can consistently meet that. So it's the mean minus those 3 sigmas. So from the central mean minus 3 sigmas to the lower spec limit. So if we have mean and we have the standard deviation calculation, we can then say the lower spec limit for that data would be blah. As long as you've got the right considerations in that calculation in terms of quantity of test, etc. Quantity of test in particular is really important. That's where this value can come from. So if the process is in control by a normal SPC chart, then this process mean is centered. So if the centered CP is then the upper spec limit if we have one. And there's a reason why we might not have an upper spec limit. Many reasons why. Materials data, we don't often have an upper spec limit unless it's a measurable thing like a chemistry. Minus lower spec limit divided by that 6 sigma, which is then 6 standard deviations. That will give us a CP value. So if it's less than 1, the process variation exceeds the spec, which means that the spread is beyond those limits. If it's exactly 1, it's just meeting those 2 specs. And if it's greater than 1, it means that we have a range which is smaller than the upper to lower spec limits, which puts us in a bit more of a happier place. So that's the spread of the process related to the spec, but it doesn't address how well the process averages. So this is a really interesting thing as far as materials and specs can be interesting. We had loads of suppliers at Airbus who had exactly this. Looks really good, but if we have the same spread, hopefully you can see the mouse moving, if we have that same spread, but it was all moved over considerably because there was no upper spec limit, but we had the same width of distribution, which supplier is better? Well, actually, in real life, you want to look at the supplier who's furthest away from your spec min, not necessarily the supplier who may be even more consistent with a narrower width, but be closer to that spec limit. So that's when we start to look for CPK. So this measures process variation, but it also considers the average, the position of that average. So, okay, CP less than 1, CP greater than 1, that's how we are versus the limits. But this CPK will take either the CPL or CPU, which is the CP calculation based on just the lower or the upper limit. So the CPL is the mean minus lower spec limit divided by 3. So that means that if we only have a lower spec limit, we can use that calculation to give us the same value. And then what we're looking for this kind of 1.33 target, or you can set goals of around 2. But what we can do with this CPK is look for the distance versus that lower spec limit. So it gives us a calculation based on how far away that is. Hopefully that kind of makes sense. I don't want to go into too much depth because we will we'll cover this again in the final year, and anyone who stays for the Masters will work with it a lot more, but I just want you to be aware. So all of our materials data is from a lower spec limit. If we had a load of coupons and tested them, our mean will always be, or should always be, 3 standard deviations higher. So for your assessments where you've been given some data and you've worked out mean and standard deviation, what you could have started to do is plot what these graphs look like. Now, you didn't have enough tests in the end, so you didn't have enough data points to do it fully valid, but that's the start of the process. If we had a brand new material that we didn't have a spec limit for, the way in which we, in industry, that we actually calculate the minimum isn't as simple as just 3 deviations, because 3 deviations doesn't factor in the knockdown of quantity of data appropriately. So to calculate statistical minimum, we do something called A-basis value calculations, or S-basis value calculations. These are both based on something called the MMPDS, which is what used to be called the mil spec. You can get copies of this on Google. If you just Google MMPDS PDF, then there's loads of questionable versions. And I can send you the sections that you might want to look at separately if you'd like to look into this a little bit more. What we've got really is for ultimate yield strength, which are things that we've looked at before. Compressive strength, that also fits in, but it's not something that we really work with often. We can calculate from a data set, really should be higher than 100 minimum data points. But we can calculate what is the true minimum to give us the high level of confidence. So to do that, what we normally have is A-basis data. So what we want to say is 99% of the population, we expect it to exceed or equal, and we want to have 95% confidence. So 99% of the population, 95% confidence, or a B-basis value is 90% of the population and 95%. So if we want to give ourselves as much of a guarantee as possible that our data is with 99% of the population and 95% confidence meets that minimum value, this is the calculation we will follow. So this A-basis value, we take the mean of our data set and we subtract K99, which this is the official term. It's called a one-sided tolerance limit factor. Basically, it's a knockdown based on how many data points you've got, and that's given to us from the MMPDS. It's on the next page. And we multiply that by the standard deviation. So it's a bit small, but if we have, let's say we only have 5 data points, our K value is 5 and a bit. So if our standard deviation was 50 megapascals, then we have 5 and a bit, so we'd end up with our mean of our data set, which let's say it's 1,000 megapascals, minus 5 and a bit times that 50 standard deviation. So we end up with an A basis calculation of less than 750 megapascals. If we did exactly the same test, but we did it 100 times, then we dropped to 2 and a bit. So then we can reduce that just because we give ourselves more confidence from more data. You'll see that even for, what's the highest we've got 180. So 180 is 2.5, and then 90, 2.7. So as soon as you get 2.7s, as soon as you get into the kind of towards the 50 range, you're there or thereabouts. You might have heard me say before, minimum of 3 data points, because before 3, you have so few data points that the effect of these things is, in terms of confidence, is just crazy. And we used to have a rule of a minimum of 16 data points for any kind of validity, and that gives us a 3 and a bit times knockdown. Not ideal, but that's a good start. So what I'm going to leave you to do at the end, we'll come back to that, but using your assignment 1 data, I'd like you to dig that out if you can. You've already got the mean, so then using this table, the K99 value for your quantity of data points multiplied by the standard deviation, what is the actual A basis value? So your data that I've given you, the A basis value should be pretty easily calculatable from your data that you've got, and that'll be interesting to see. And the important thing from this is the way in which we calculate what the spec limit is, the spec min. That spec min is what we then see on all of the data sheets that we're looking at. So if we can understand this calculation, that allows us to have that confidence of where that data's come from. Final bit then before I have a little minute and just check if everyone's okay. So design of experiments. This is quite an interesting method in which predictions are made on data. When we're making predictions, we can normally only make them quite simply for a single point. So we can predict the next ultimate tensile strength of a mechanical test. What a design of experiments can do is it can look at things in a multifaceted approach, and it can start to, using software mostly, we can actually look for, well, actually, what's the prediction of the next ultimate tensile strength, but we need to factor in the material, the manufacturing process, the temperature, the time in which the test is held, the rate of the test. And what we have to do is fill this design of experiments tool with all of these different data points, and it looks for patterns and correlations, and it uses an absolute plethora of statistical methods to look for patterns of performance or patterns which correlate what's going to happen next. So design of experiments is something which is really interesting for material scientists in particular, but also process analysts. Again, something that I'd hope we touch on more in the final year and into the masters. Good. So if I just get you all back open, I'll just unmute you all. Is that okay? It's a bit deep and heavy, isn't it, for the first day back in electronic classes? But that all seem okay? Does that make sense? Any questions on that point? No? Everyone happy?
Yeah, it's fine.
Yeah,
it's fine.
Yeah.
Good. Okay, so I'll go on to the knockdown factors bit now then. So all that stats is really important. It's an important grounding into what we do with materials data. And the next big thing that I'm expecting you guys to do a lot more of next year is when we're looking at data, we now know kind of the origins of where these spec min test data come from. When we get given a bunch of data, we can then work out what the specification minimum would be. We can work out confidence intervals. And like I say, I'm expecting you to go back and do that calculation when I finish going through these next couple of slides. What I now need us to think about is trying to turn this word of materials into a three-dimensional thing or a part. So we don't just blindly choose a material and apply it on SolidWorks and say that that's the material we're going to make it from. We already know that we will choose a material based on the force and the potential area in which we need to operate in, and that will give us a stress value expectation, and that can give us then an idea of what material to choose. The other thing that we have to think about is, well, how will we actually make this part, regardless of the material, because materials behave differently under these three main considerations. So different materials in the physical process of being manufactured actually can have a very different effect. So processing titanium is pretty difficult. You end up having to generate quite a lot of heat, and you also have to put a lot of force into it to get it to move or change shape. Aluminium, on the other hand, is really easy to work with. What you find is then, if you have to put a lot of mechanical effort and thermal effort into the part, if it was titanium versus aluminium, then there's potentially more knockdowns from processing on titanium than there is aluminium. And what that knockdown is it's a percentage drop in mechanical performance expectation based on what's happened to it. If our materials data is always very one-dimensional and it's based on test coupons, then actually when we process this as an engine block or as an upright or a wishbone or whatever it might be, that process will have an effect because the shape isn't consistent. The shape of a coupon is, the shape of the final part isn't. So there are three main knockdown factor areas. When we're processing a material, something that will give us a reduction in life or more scatter in that performance is a process knockdown factor. We then have environmental knockdown factors. So this is the environment in which the part is usually operating. So for example, we go back to that upright example, always exposed. Titanium's much better at resisting corrosion than aluminium. Aluminium, when it's close to other parts, as we'll talk about in the next couple of slides on assemblies, it can have a lot of issues. So what environment is the thing operating in? Very high temperatures, low temperatures, cyclic temperatures, all of those things have to be considered because, again, different materials act differently in those conditions. And then also loading, if in particular for dynamic loading, so we've mentioned it a few times this year with fatigue. Some materials, they might be equivalently strong in static, but actually they have a much lower fatigue life because, again, the crystalline structure of material allows it to be more or less susceptible to fatigue cracks. So that's the first step of things we have to consider on an individual part, but also specifics then with the processing. A couple of examples here. So if your process is well understood, as in it always gives us the same output, back to the same point we just talked about process capability and process confidence, then that can give us confidence that the process isn't going to change the material. However, some processes are naturally more variable than others. So if we machine from a billet, cast, then we work it and machine it, well, in the case of machining from a billet, the billet should, when it's machined, give us a final finish. So we're saying 3.2 RA, that's just an expectation minimum in aerospace. So if we machine both of these parts at the start, at the end of the processing, they'll have the same expectation. They should be able to meet that because that's down to the machine tool. Machine tools are very consistent. If we have a billet, billets pretty much never have pores because their process controls the development of microstructure and also prohibits pore growth. Whereas a casting, we know, is very porous. So what you can end up having is a cast part then has to be worked to give it the equivalent amount of limited porosity as a billet part. That process is two separate processes, both of which have risk, thermal risk, environmental risk, etc. So if machine from billet, we have billet and machine, and then we have cast working machine. So 3 processes for one, 2 for the other. Pretty much in a nutshell, any minimal amount of processing, maximum amount of performance. So the more times we have to mess with something, the more knockdown it will get. So combining the fact that something is billet and then machined, maybe we'll have a very low knockdown, maybe we'll have no knockdown at all. Maybe we trust the billet data, the machining has no effect, so we say the knockdown factor is 0, there is no knockdown. Castings, however, because they're porous and they have to be worked, because castings have much more variability, then maybe we have a knockdown factor of castings of 15%, 10%. So if we did a sequence of testing on both of those conditions, even if they had the identical mean, our knockdown factor would mean that the cast versions would be lower performing just because of confidence, not because of physical performance. In reality, cast parts normally are lower performing than billet, but just for the ease of an example, if they were both tested, both the same, casting has more areas in which processes can be affected or can affect it, therefore it would have a greater knockdown factor. Then if we have a cast part which is then not worked, so it doesn't act like a billet, the machining as above, we're pretty high confidence that machining is good, but if the casting didn't have any additional work like hip or like being physically worked, that casting would then give us this 10% knockdown. So if we cast something, we work it and then machine it. If we just cast it and then we machine it, that's where we get this knockdown. An interesting one, so if you are looking at the regulations for aircraft, so the European aerospace regs, the American aerospace regs, and the CAA is the British variants. If you use carbon fiber, in particular carbon fiber, but I think that it is a sweeping statement against composites, you do have a knockdown factor of 40%. So even if you have, I don't know, 1,000 megapascals tensile strength as your mean, you have to apply a 40% knockdown factor to that value before you can use it. And that's because the aerospace organizations don't have confidence in the processing, or they don't have confidence in the consistency of production. So then the final thing that we have to think about a little bit is combinations. So what if we have, for example, a cast part which is attached to a machine part by a fastener? So is there a knockdown factor for the casting? Yep. Is there a knockdown factor for the standard machine part? Maybe a little tiny one, maybe not. What happens then when we fasten them together? Do castings crack easier than billet parts? Yep. Is the fastener a weak spot, or is it the hole? How's the fit? Is it an interference fit or not? So we actually, just from attaching 2 parts together, we might then have an assembly knockdown factor. Next example then, composites attached to aluminium. So composite knockdown factor is 40%. A fastener, we might have found a fastener percentage is 5%. We don't like fastening things, so there's a knockdown there. A machined, nothing. And then we have this environmental knockdown, because if aluminium is connected to composites, actually aluminium will readily corrode. So we might have a 10% knockdown. So then all of a sudden, our total knockdown could be 55% for that performance of that assembly. So these are reasons why we normally avoid exposed aluminium, because actually, even though it doesn't heavily corrode, it does corrode, and it's worsened by certain types of environment. Another example then, so a composite part attached to a machined and protected aluminium by adhesive. So the same knockdown factor for the composite, the same for the machined, but actually this protection, this adhesive and the protection means that that environmental factor, which might have been 20%, might have been 10%, that can be reduced significantly. Do we have high confidence in adhesive versus fasteners? Probably not. So then that would then actually make that worse, or make those 2 versions an equivalent. Hopefully that makes sense. Now, what what we need to try and do is put this into practice. The idea at this stage in real life was we was going to go into the workshop and we was going to have a look around some cars, because there's some really good practice and there's some really dodgy practice on things like the McLaren tubs in particular. They're quite interesting. And we was going to come up with some numbers, but that's going to be quite difficult. So what I'd like us to do is I'll leave the Zoom meeting open so you can come in and out of it as you please, but I'd like you to go and do that A-basis calculation. And if you want to have a calculation of an example assembly that you can think of, or you might have a picture of, feel free to do that. And I'll linger around in this Zoom meeting so that if you need anything, you can come back and ask some questions. I'll leave that on the screen, but I'll unmute everyone.
What am I avoiding?
Hopefully that makes sense. So has anyone got any questions?
No, not at all.
Okay. So there's no registers anymore because these sessions are quite flexible. So I'm going to stop the recording.